and successes, but they are not very well documented. That is the problem. So there's a whole INSA, for example, runs a whole Indian Journal of History of Science, where you get lots every month or every couple of months, you get very nice articles on history of Indian astronomy and Indian science. But again, they use, for example, Sanskrit words. They expect you to understand the Sanskrit meaning of the word and stuff like that, which is not easily understood by somebody who is not within the culture. We don't have good general popular books in English for astronomy.
Okay.
There was one book brought out by the planetarium, I suppose, in the Indian Astronomical Society about Indian astronomy.
Yeah, so I have, for example,
it's out of print now.
Yeah, but National Council of Science Museum made me write a book also on perspectives on growth of astronomy in India. So there are a few documents. They are not as widely available. My book, for example, is just published for private circulation by National Council of Science Museum, NCSM, and it is not available commercially. We have recently brought out the whole handbook of Indian astronomy, which we think should be more easily readable to foreign audiences. But again, it's a private publication of Tata Institute of Fundamental Research and IIT Bombay. We are now trying to commercialize it and stuff like that, but things are not moving as fast as we should. Basically, if a foreigner comes and says, okay, Indian culture interesting, I want to know about Indian astronomy, give me a book, he would really struggle to find good books. Quite funnily, the best books on commentaries on Indian astronomy are from the British period. In 1800s and 1900s, some British scholars have come and taken great pains to write Indian astronomy in English. And these are published by Archaeological Survey of India. And they are by far the best books I have, which give you good technical details of astronomy, except that they don't have a popular flavor. But if you are seriously interested in technical details of Indian astronomy, and if you don't want to sit and go through Sanskrit, take the books that were published by Britishers, which are being sold by Archaeological Survey of India, and they give you all the technical details you want, very beautifully laid out. But again, they are not for common man. But as with many things Indian, the best translations in English are available from foreign authors. But that's the tragedy. We just don't have enough people to go around to write books on these kind of things.
Vaya, may I interrupt here?
Yes, sir. Yes, sir.
Did you emphasize that the progress in Indian astronomy from the days of Aryabhat was largely concerned with dynamical astronomy?
Yes.
In the sense, our astronomers, Aryabhat, Varahamir, Bhaskara, they were more interested in predictions of eclipses, okay, and the planetary orbits and such aspects. The physics, chemistry with astronomy did not come in until late in 19th, 20th century.
Yeah.
In fact, physics and astronomy really gave rise to the subject of astrophysics. And later on, we had astrochemistry and now astrobiology.
Yes.
So that is all modern development in the 20th century. So that's one of the reasons why the history covered in Sanskrit treatises of the earlier development in astronomy due to Aryabhat, Varahamir, Bhaskara, all that goes back to the middle of the 4th century, 5th century, until the 12th century.
Yes, sir.
Until the days of, what's the Keralite?
Kerala school, basically, the Kerala school. But basically, calendrical purpose was a primary purpose for
that's the main purpose. Right.
You have to get the data done.
They hired in the courts just to predict the calendrical events.
Exactly.
Indian astronomy rather quickly merged into astrology. That was the...
Unfortunately...
By the way, I have a very strong opinion on that Indian astronomy was not designed for astrology. The idea that astronomy could be used for astrology comes from Yavana astronomy from the Greeks. If you look at Varamira's work, he has actually defined what the syllabus for an astronomer should be. And he does not say that astrological prediction should be part of something he should know. So
Can you circulate that? Can you circulate?
Yes, sir. Yes, sir. So in the PPT about archaeoastronomy that I have sent, there is one slide that defines the syllabus. And the textbook, it is in Subarayappa's book. That entire slok is there in Subarayappa's book.
Okay.
And he is very clear that an Indian astronomer should be able to determine latitude, longitude, solar solstices, eclipses, etc. But he does not say should be able to make a prediction. The only thing he says about people is that should be able to teach to other human beings.
That's right.
It was the era when the current part of Panchanga came in.
Yes.
Yeah.
Panchanga is not astrological.
No. Current part.
Yes. So Panchanga claims to have its original in Surya Siddhanta, 12th century AD.
Yeah.
It has its problems because of the fact that some of the subtle effects of movement of the earth it doesn't take into account. So if you stray with Surya Siddhanta, you actually drift away from the current date.
Yeah, they are not accurate.
Yes. So we have done some work to show that if you just add an additional term for precession to those equations, you can make a modern Panchang using Varamira.
Which agrees with the position. Yes, sir. Good.
So, which is...
So now I think we should proceed. Our Professor Dr. Chitre is here.
Yes, 36 people are in already.
He will not like it to be mentioned, but it's our pride. He is Padma Bhushan Professor Dr. Shashi Kumar Chitre, who worked for TIFR for very long years, and then he was at the Mumbai University in Center for Basic Sciences, which was the Center for Excellence. And today he is here. But I would want Dr. Mayank Wahiya to tell you a little bit, at least a little bit, about his theoretical astrophysics work.
So, Professor Chitre, it's a pleasure and a privilege to introduce Professor Chitre. Mugdha already said that Padma Bhushan, but I think Padma Bhushan is a very small part of the recognition of his work. Professionally, he is one of the most outstanding astrophysicists of the country today. He got his early education in Cambridge. He was 1 year junior to Narlikar, if I'm not mistaken, and he was in the same 3-4 years junior to Amartya Sen. And so he grew up his academic qualities in these environments, and since then he has never looked back at excellence. He has done some profound work in thermodynamics of stars and evolution of stars, and then on solar oscillations and the structure of the sun, as well as on gravitational lensing and large-scale structure of the universe and all that. He has produced a large number of PhDs who have all gone on to do excellent careers in himself. So he not only has done great work himself, he has also left behind a large legacy. I had the privilege of being guided by him for some time when we were in TIFR together, and he's one of the most profound astronomers of the country today, and it's a privilege to welcome Professor Chitre to come and give his talk today. Professor Chitre.
He was one of the few who in those days went abroad for education and then came back.
And I should also add CBS. After his retirement, he started Center for Basic Sciences for undergraduate and PhD program, and is one of the finest institutions for undergraduate science. So just as countries started IITs for engineers, the Center for Basic Sciences is designed to create the scientists of tomorrow, and he has led it with distinction for now 6 or 7 years. And it has produced some really very fine students who should be manning India's scientific studies in future.
Well, Chalo, thanks Mugdha Tayi and Vaya. Friends, you must have realized these are my friends talking about me. I mean, I have both friends and enemies. You haven't heard my enemies yet. So in any case, very flattering to hear from one's friends. I mean, history of what I went through in my academic career, basically. Now today, friends, I have chosen a topic in the form of a question, namely, is there intelligent life elsewhere in the universe? You realize that I'm assuming there is intelligent life here on this planet, and we are now asking the question, does it exist elsewhere? In fact, it might be difficult to find intelligent life here on this planet than it might be elsewhere. But we still haven't hit on that extraterrestrial civilization or alien life which is as advanced as we are. And in fact, the main theme I'm going to develop here is that in the form of a question in the 13th century, St. Albertus Magnus, a medieval scholar, had asked this question: do there exist many worlds, or is there but a single world? This is one of the most noble and exalted questions in the study of nature, which is true. This is really a reflection of what the Greek thinkers had debated for a long, long time. And in modern form, we have just resurrected that debate. We still don't know. There are some of us who believe that there's a strong possibility that there might be life elsewhere because the universe is so extravagant in scale. There are billions and billions of galaxies, and the chances of some of them hosting a good Earth, good sun, okay, what they call the Goldilocks zone, not too hot, not too cold, where life may arise, chances of very high. The basic theme we wish to develop. Next slide, please. Varya, could you have the next slide? So that's the question. You have infinite extent of the cosmos. We can see that we don't know if the cosmos is finite in extent or is it infinite. Plurality of worlds and principle of plenitude, what can exist here on Earth must exist elsewhere too. This is an extrapolation. Now, plurality of worlds, some of the medieval scholars did not quite like. For the simple reason, this is a theological reason. The Christian scholars in the medieval era thought that if, for example, there are other civilizations, they would also need a savior, and savior is unique. And if Christ has been the savior for earthlings like us, then how can there be other Christ? So they dismissed it because of the singularity of Christian religions, beliefs that Christ is unique. So, but earlier in the 4th century BC, in fact, Metrodorus said that to consider the Earth as the only populated world in infinite space is as absurd as to assert that in an entire field of millet, only one grain will grow. So he obviously had thought on probabilistic ground that it is unlikely that only life would have flourished here on this planet. So let's go to the next slide, please. Well, here is a schematic of our solar system. Let's start from our neighborhood. I'm assuming that you have covered some of this ground, that this is a reminder before we come to the philosophical aspect. I hope I can cover this all in one lecture, one presentation. So the sun, the central body, with its retinue of planets and some minor bodies like asteroids and comets. And here you have 8 planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And of course, Pluto we have demoted. It's a minor planet because there are other Pluto-like minor bodies in the solar system. So IAU in its wisdom voted against Pluto as being considered as the 9th planet. And then you have comets, of course, and asteroids. So these are what the bodies which make up the solar system. The question now you have to ask is there a possibility that there might be life in some form? You don't have to think of only the carbon-based, very developed form of life as we have here on the Earth. There might be life which is based on ammonia, which might be based on sulfur, okay, or silicon for that matter. So next slide should tell us, when we go through the birth of the solar system, how did the solar system come into existence? There were a number of theories, way back in 1755, Kant, and then later on, Laplace in 1796, postulated the nebular hypothesis, which is just about right and close to what the modern belief is, that you have a gas cloud, the gas cloud collapses under its gravitational force, the central body goes into our star, the sun, and then the debris left around in the system of planets which we have leaves behind the solar system. Another theory which James Jeans propagated at the turn of the last century was that a dancing collision with a passing star with the sun tidally captured material, pulled out material from the sun, and that debris was left, which eventually formed planets. And the third and more modern version is that the birth of our sun is in the aftermath of a spectacular supernova explosion. So near where our proto-solar nebula existed, a supernova explosion took place. I'll come to the supernova explosion later, but you may already heard from Professor Vaya. Actually, this talk is based largely on what I had borrowed heavily from Vaya, from his slides, and from the up-to-date information from the Kepler and other recent satellites. So I hope you are hearing me, okay? Because I'm just going to run through our solar system, show you the planet Earth. By the way, is there any question you'd like to ask me right now, or shall we wait till the end of the talk for questions?
No, the end of the talk, please, sir.
Okay, all right. So here is our Earth. Blue, pale blue dot. Okay, and if you were to look at our solar system from a distance, from outside, this pale blue dot would fade out in this, the sun will outshine it, basically. This is like a fly next to a searchlight, okay? So, and this is the planet on which life has arisen. Unfortunately, at the rate at which population is growing, in 30 years, we will double the population on this planet. In another 1,000 years, the number of people on this planet will almost match the mass of our whole galaxy. So you can imagine our planet Earth, or Mother Earth, is not going to survive too long if we don't take care of the inordinate growth of population. By the way, is it coming through the talk? Shall I slow down, or is the pace okay for you? Mugdha?
Absolutely fine, sir.
Excellent. Next slide, please. So let's run through the solar system quickly. Moon, our neighbor. Well, manned and unmanned lunar missions have succeeded. In 1969, in fact, man landed on the moon, Apollo 11, first appearance of a man on a distant celestial body. And we have now recently, after successive missions, discovered a pond of ice hidden deep inside a huge crater on the south pole of the moon, which is away from the sun. So the ice has survived. And here is the footprint of Neil Armstrong's shoe on the moon lunar surface, which is of course still survived since the moon doesn't have any atmosphere. That's not going to be easily washed away. Next slide, please. All right, here is Mars. Network of Martian canals, you can see if the slide is showing, with the polar caps, which almost resemble our caps, northern and southern, but that's not water, frozen water. It is frozen carbon dioxide. So polar caps are really carbon dioxide and not frozen water. In fact, atmospheric pressure on Mars was 1/100th the Earth's atmospheric pressure, at which liquid water would quickly evaporate. It won't survive. So Martian atmosphere is mainly composed of water vapor and carbon dioxide, oxygen, and no trace of nitrogen. So it is unlikely the kind of life which we are used to, which is based on carbon, oxygen, nitrogen, is likely to exist on the moon, which is a kind of disappointment. Viking mission sent in 1976 did not find any evidence of organic life, but there may be single cell microbes detected in Martian rocks found in the Allen Hills ice fields of Antarctica, for example. And here is the Martian soil, all red soil. And here is one of the meteorite fragment which we discovered on the, what's it called, ALH is a number 84000, which failed. It was presumably a remnant which arose from the Martian surface by a hit, either a comet or a meteorite, and that traveled through the interplanetary space and eventually landed in Antarctica. So maybe life does exchange itself between planets. So the question is, where did the life arise here on Earth? Was it mainly in Darwin's warm little pond on the Earth's surface, or was it planted here from outside? That's the question which we'll address later. Next slide, please. Here is Venus, a beautiful evening star, though very uncongenial in the front. It's like an inferno, boiling hot, crushing pressures, presence of corrosive gases, sulfuric acids. So the Venus is unlikely to harbor life in any form, except that some microbial life could exist in Venus's atmosphere. The thick cloud extending to some 40 miles above the surface acts as a blanket and traps the sun's radiation. So that's why the Venus's surface and the cloud cover extending to 40 miles is very hot. So surface temperature is about 900 degrees Celsius and pressure is nearly 100 times our atmospheric pressure. So this kind of uncongenial circumstances are unlikely to harbor our kind of life, though microbes might exist. Next slide, please. So Jupiter. Now Jupiter is an interesting object. Of course, we know that's the dominant planet in the solar system. Jupiter, it almost missed becoming a star. If Jupiter's mass had been little larger, it would have triggered the thermonuclear reactions inside, and it would have shown on its own, which is what the definition of a star is. So Jupiter's atmosphere is like a hanging zoo, if you like, a vast chemical laboratory containing a mixture of elements like ammonia and water vapor, from which primitive forms of life probably arose on the ancient Earth. Precursors, if you like, of complex microorganisms. In fact, Stanley Miller and Harold Urey produced such organic amino acids from such a mixture of ammonia, methane, water vapor, and bombarding the mixture with ultraviolet radiation. But of course, you mustn't forget, radiation is a far cry from creating the first cell and then later on proteins and what have you. So traces of oxygen are detected on Callisto, one of the moons of Jupiter. And Jupiter's moon Europa, for example, shows evidence of 100-mile deep oceans containing 3 miles deep as much water as Earth. So I think we have to watch out for the moons of Jupiter. They might harbor life, Europa, Callisto, and if that is so, that may be a remote evidence that indeed, besides the Earth, where we have advanced forms of life, there might be microbial life. This Jupiter. Next slide, please. Saturn, of course, with its rings, very impressive. Next slide. I'll have to rush now. Saturn's moon, Titan, the icy moon of Saturn. Next slide, please. Here's Uranus, Hubble Space Telescope picture, and Neptune. So let's move out of the solar system now, and let's go to the wider features of the interplanetary space we have covered. Let's come to the interstellar space. You see, our galaxy, you must have heard, or perhaps Vaya hasn't covered it yet, but our galaxy consists of some 200 billion stars. But besides stars, we have gaseous clouds and molecular clouds also. And these clouds, like the Orion Nebula, which you see here, are the nurseries where stars, along with their planetary retinues, are taking place. So stars and planets are born out of gradual compression of tenuous interstellar material made of gas and dust. So Orion Nebula is a cloud which is capable of manufacturing some 100,000 stars. And here is Trifid Nebula, likewise made of gas, and you can see the dust lanes. So these are the nurseries out of which stars, presumably along with their planetary systems, are being formed. In fact, later on we'll see a picture from Hubble Space Telescope from the Orion Nebula. If you go to the next slide. Next slide, please. Skip this. Yes, here is the birth of stars and planets in the Orion Nebula. You see disks around the proto-stars which are forming, and disks are the debris out of which the fresh planetary systems are going to get formed. So here is the gaseous cloud. Here is the central body out of which planets are forming, and the debris left around is the debris made of dust, okay? And that is where you're going to get the planetary systems formed. So this is just one example of Orion Nebula, Hubble's picture. Next slide, please. So here are the pillars of creation of star formation in the Eagle Nebula. And here at the tip, you will get out of the gaseous clouds and the dust, new stars forming. So this is the cradle for the formation of stars. So but just as stars are being formed and they're getting born, they also grow old and die. How does that process occur? For example, here is the death of a star in the Crab Nebula. It's a very famous picture of a massive star, roughly of the order of 20 solar masses, at the end point of its thermonuclear evolution. See, basically, history of a star is nothing but a chemical evolution. Stars are made largely of hydrogen, which is the primeval element. In fact, the belief is that in the early universe, in the first 3 minutes, you had the lighter elements, hydrogen, deuterium, tritium, and helium, up to lithium and beryllium form. The rest of the elements are all cooked and manufactured inside stars, because stars have the right conditions, dense enough and hot enough to cook, to fuse. For example, hydrogen is fused in sun-like stars, and hydrogen gets converted into helium, helium into carbon, oxygen, and the higher elements, carbon, nitrogen, oxygen, silicon, aluminium, sulfur, in more massive stars, and eventually in more massive, like 10, 20 solar mass stars. These are the initial masses, remember? What we call the progenitor stars. With these masses, they have basically an onion-like structure with iron core, iron, nickel, metal core in the center, and then you have successive shells, onion-like, of silicon, magnesium, sulfur, potassium, so all the elements which are essential for life. So they are cooked inside massive stars, but stars are not selfish. They don't contain and keep the elements which they are manufactured inside them, but they throw them out in spectacular explosion of the kind which you see here in the Crab Nebula. So the shock wave which goes out as a result of the explosion goes out and then presses against the tenuous nebula like the Orion Nebula and Trifid Nebula, out of which the next generation of stars are formed, but they also incorporate the elements which have been cooked in the earlier generation of stars. So in the sense that stars had to die before new stars are formed, they take birth, and they incorporate the elements which have been cooked in the third generation, what we call second generation, first generation. Our sun is the first generation, population 1 star. Before that, population 2, and right near the birth of the universe, the population 3 stars, which are massive. Next slide, please. Raya, thank you. So there's a connection between the death and birth of stars, you see. So birth of our sun is supposed to be in the aftermath of a spectacular supernova explosion close to the site of our protosolar nebula. So in a way, as George Waugh, the biologist, said, we living beings are a late outgrowth of the metabolism of our galaxy. So in a way, stars are not very selfish. They go through their life cycle. Basically, out of this tenuous gas clouds, like what you saw in the Orion or Trifid Nebula, the gravitational instability of the genes takes place. Gravity pulls the gas clouds in. The gravitational energy is converted into thermal energy, and density goes up. So does the temperature. So until the temperature reaches of the order of 10 to 15 million degrees, and densities of the order of 100 to 200 grams per cc, the furnace, thermonuclear furnace inside, in the core of the star, doesn't get triggered. So to trigger furnace, we convert it into helium, helium to carbon, nitrogen, oxygen, successfully building heavier elements until iron only. Beyond iron, elements cannot be cooked inside star. Many will ask me, where do those elements, thorium, uranium, platinum, they come from? Lead, bismuth for that matter. We'll come to that. So born out of the ashes of dead stars is the story of the evolution of stars. As I said, light elements like hydrogen, deuterium, tritium, helium, beryllium, and lithium are manufactured within the first 3 minutes after the birth of the universe. In fact, I would recommend you to read Stephen Hawking's, not Stephen Hawking, Stephen Weinberg's book on Stephen Hawking's on my mind, because this shelf, his book is there. If you don't believe it, let me show it to you. So, why I would know Stephen Hawking? Because he helped me in showing Stephen Hawking around. You should ask Vaya that story. Anyway, let's go back to the previous slide. Vaya, go back a slide, please. So light elements, as I said, are cooked in the first 3 minutes, which I would recommend you to read from Stephen Weinberg's First 3 Minutes. Very nice book. But the life history of a star is really characterized, and this is the theme you should take home, by continued contraction of its central regions with halts caused by a succession of nuclear energy generation when the density becomes high, more than 100 grams per cc, and temperatures become high, million to 100 million degrees. So hydrogen gets converted to helium in sun-like stars at temperatures of 10 million degrees. Helium goes into carbon oxide temperatures, and carbon oxygen in more massive stars at temperatures of 100 million degrees manufacture neon, silicon, magnesium, and later on, in more massive stars, you get iron, nickel, cobalt, the metals. So the evolution of atoms, remember, is associated with the evolution of stars. Now, stars have to die, unfortunately. They spend their whole lifetime cooking these elements for us, which are vital. Oxygen, carbon, nitrogen, sulfur, phosphorus, they're vital for our survival. Calcium in our bones and iron in your blood, they're all manufactured in massive stars in remote past. So in that sense, as Carl Sagan used to say, that we are made of star stuff. Because the cycle which you see here, we have condensation of young bright stars like Orion, Trifid, then go back here, and the Eagle Nebula. Then you start to forming stars, nucleosynthesis of heavy elements. They explode at the end point of the thermonuclear revolution and give back the elements they are manufactured. Then mixing of these complex atoms with interstellar clouds of gas and dust, out of which the next generation of stars are formed. So this is that Punarapi Jananam, Punarapi Baranam, Punarapi Janani, Jatare Shayanam cycle goes on, of birth and death of stars. If Mugdha Karni invites me again, I'll give you a talk on birth and death of stars and their rebirth. Because interestingly, initial phases, the stars depend on an energy source they draw from the gravitational force. The gravitational energy is converted into thermal energy. The thermal energy basically, and of course, the density scales as mass divided by R cube. As you know, mass is volume into density, and temperature scales as mass divided by radius. So because of that, basically, once the thermonuclear furnace is triggered, you get this cycle going on. So stars had to die for us to inherit the elements like carbon, nitrogen, oxygen, phosphorus, calcium, iron that are so vital for our life process. So this is one point which you should really keep in mind. Next slide, please. So that prompted, in fact, it has been on our minds for a long while. Only 20 years ago, when Kepler satellite was launched, we were looking, earlier we used to think that Vega has a planetary system around, or for example, VB8 was another star which had a planetary system around, or Beta Pictoris had this planetary disk out of which planets are being formed around the star. But 2020, as of that, Vaya pulled out for me that there are 4,160 confirmed exoplanets, planets beyond our solar system, in 3,090 systems, stellar systems. 76 systems having more than one planet, extrasolar planet. These are a large fraction of stars seem to have planets around them. So we didn't know this 20, 30 years ago. And suddenly we realized that there are extrasolar planets which are going to be in our galaxy at the level of billion such planetary sites. And now you will ask the question, what are the probabilities that planetary systems will harbor life of the kind we know? Or will it be only in the microbial form? You should never assume, because this is our anthropomorphic view. Our life is based on carbon chemistry here on the Earth, but there may be sites in the galaxy where life could be based on ammonia, sulfur, silicon, who knows? A large fraction of stars seem to have planets around them. Some are Earth-like, not all. Quite a few of them are Jupiter-like, massive. About a dozen are known to be potentially habitable zone. See, we want to look for habitable zone. Good Earth, good sun. Not too hot, not too cold at the surfaces of planets, like what our Earth is. Good Earth, good sun. On such sites, chances are in the habitable zones, life might arrive. So the nearest planet, go back, nearest planet is around the star Alpha Centauri, about 4.4 light years away, while the nearest potentially habitable planet is 20 light years away from us. So now, why are we doing all this? See, eventually you realize that it will make a vast difference to our philosophy and outlook on life if we find that indeed we are company in our galaxy itself. Forget about other galaxies, extragalactic domain. If that is so, then there are reasons why we should try and contact them. Next slide, please. Here, something I borrowed from Vaya, of the stellar system as imaged by the Hubble Space Telescope. The light from the central star, and there are 3 planets around. So we are now come to that. Now you will ask me, how do we see this planet? See, as I said, it's like a firefly next to a searchlight. Pale blue dot next to the sun, which is outshining our Earth. Then how do you see? Next slide will show. There are these astronomers have figured out. For example, suppose you have a star and this planet which is going around comes in front along the line of sight of the star. Then the light of the star dims a little. Okay? There's a dip in the light curve. And that gives us an indication that yes, there's a planet. If there's another planet, that will produce another dip. This is the transit. Then there's the Doppler method. For example, the star around which there are planets orbiting, then the star will wobble around its barycenter, or the center of mass of the orbiting objects, and that gives an indication. And then there is a third method called microlensing, which perhaps I shouldn't cover here. Microlensing is around the star, there could be a planet, and that planet can lens gravitationally the background. That immediately tells you that there is a planet around. But that's a somewhat difficult method to follow. Next slide, please. So these are the methods. And Kepler Mission, which was launched in 2009, really gave us a bonanza. Okay, and it worked until 2013. 4 years, we got it revolutionized practically the whole subject of both astroseismology and extrasolar planets. Asked me, what are the future areas young men and women should, and even old people like me, should aspire to work? I would say cosmology, that is because of the modern technology and the satellites and various missions which are from space observing the cosmos. There's so much data that is coming down that one should analyze that data. So that is one area. And what Martin Rees tells me, that another area is extrasolar planets. So remember this, what Kepler Mission has left for you is a legacy. Let me just take this call. Hello, how's Sammy? Okay, I'll ask Latata to come down. So the mission, the Kepler mission, was designed to find transiting planets, okay, for around 145,000 stars by monitoring their light for 3 years. It was sensitive to light fluctuation to 1.10 to the 5. And Kepler found in the number of host stars with planetary systems around, so which was the credit, apart from doing astroseismology, which is our field. I mean, research with Antia, is helioseismology and astroseismology. So I think basically science has progressed, and as I was saying, cosmology, huge data sets which are coming down, which you should analyze with numerical methods. For example, here, only in 20 years, we have discovered so many, about 4,000 planets with various techniques, radial velocity, transit, microlensing, imaging. So I think it has paid its dividends. And it is for the young generation to now reap the benefits. You see what I mean? So next slide, please. Now here is the current potential habitable exoplanet. Here on the top, the sun, with the Earth and Mars, all right? And then you have a whole lot of systems, sort of exoplanets, sun-like, if you like, which have been detected. And we want to look for good Earth and good sun. So some of these might be, they are in the habitable zone, okay? So habitable zone is one, like the Goldilocks zone, not too hot, not too cold. And that's what we are looking for. And I think with time, I have no doubt, I hope in my lifetime, Arthur C. Clarke was dreaming. Unfortunately, he passed away before he could realize his dream, his wish. But his whole wish in his life was to see the existence of alien life. Next slide, please. Here's Kepler 62 system, and here planets around 62, whatever, I can't see it here. F, E, D, various numbers designated. And here is our solar system. So I think basically you get the picture. Picture we are trying to give you is that and the planetary system which is formed around, not all of them are in the habitable zone. Like what, for example, our Earth and Mars are. The next slide shows that. Well, here is the habitable zone. Okay, the Sun and the habitable zone is Mars, Earth, and Venus. Right distance from the parent star, not too hot, not too cold. But now, it's quite a demand that it should be in the habitable zone, but chances are high. If there are 7 planets, for example, TRAPPIST-1, maybe the next slide shows that, no, life may not be common in the universe, by the way. That also is one proviso, okay? Next slide, please, Baya. So there are problems, you have to take care of the thermodynamics, which will permit the formation of microbes, which will develop during the lifetime of the planet and the parent star. Suppose if our sun were fluctuating wildly in its intensity, then life on the Earth wouldn't have been so congenial. So availability of vital elements, which is possible only in some recent stars, lifetime and stability of our star. See, the sun had lived only for million years. Life wouldn't have arisen. It needed billion years to develop and come to this form. See, Darwin's warm little pond had ammonia, phosphoric salt, heat, light, electricity, out of which, protein compounds were formed, ready to undergo more changes, and ultimately you have the primeval cell. But that leap is colossal. How do you get the first cell from this mixture of ammonia, methane, water? Stanley Miller and Harold Urey did do that experiment. In a flask, they took ammonia, methane, water vapor and discharged with ultraviolet radiation, and amino acids were formed. But amino acids, remember, is a far cry from self-replicating cellular structure. So, lifetime and stability of the star is very important. Then salinity and reverse osmosis, high degree of ellipticity. If it were too elliptic, our orbit, life would have been difficult. Okay? Is that okay? High pressure, energetic radiation also bombarding. So we have to be shielded. Fortunately, we are shielded by our atmosphere. And it should be able to withstand hostile chemicals. Having said that, extremophiles do just that. So life is known to survive the periods of great stress in environment by hibernation or going dormant. This includes freezing temperatures, extreme acidity or alkaline, salinity and reverse osmosis or high pressures. They have found life in vents and in volcanoes even, or at the bottom of the ocean. So life seems to, in the form of extremophiles, survive. So you have to be ready that you should not have an anthropomorphic view that life only based on carbon chemistry will survive. No, life in some other forms also can survive. Next slide, please. Now the question is, what is life? Well, we assume life indulges in the following tasks. It consumes food, of course, for survival. It reacts to its environment. That's very important. In a complex manner, though, we have a relationship with our environment. It grows and self-replicates. That's an important feature for life. It produces a large number of chemical reactions. At the core of this life form is the aperiodic complexity. And we know life consists of molecules that know how to replicate themselves because it has. We see that replication process, self-replication. So that is how life, having started from microbial stage, has come in this form. I mean, we have here on the Earth biodiversity from little ant to termite to humans to huge elephants. Isn't that wonder? That nature has accommodated all of them on this planet. So why is it that we should expect we should not take the anthropomorphic view that only our kind of life we should look for elsewhere. Maybe some of ours, there may be silicon-based life, or ammonia-based life, or sulfur-based life. So we should be ready. Next slide, please. For life of any kind. And then, of course, once life is formed, the evolution of intelligent life. Evolution of life from simple self-replicating molecule structure to intelligent life is not a straightforward task. It requires evolution from molecular structure to a cell, transformation from a cell to multicellular form of reproduction to improve fitness, need to survive, need for evolution of intelligence as a survival strategy, and technological advances beyond needs for survival. Suppose you reach the technologically advanced phase, and suppose that life we decide to annihilate by getting overpopulated on a certain planet, or by indulging in biological or chemical warfare as we are now indulging at the moment. Virtually a third world war we are fighting with invisible microbes. We haven't conquered that microbe yet. Hopefully we will. So, technological advances will give us a handle, hopefully. Okay, next slide, please. So, what are the congenial conditions for habitation? Very important, even though there might be millions of sites where you might have life in some form, size with plenty of internal heat, size, isolation, and long-term stability of the parent star like our sun. Massive stars do not live long enough. Our star, the sun, lives for 455 billion years so far it has lived, and it will live for another 4-5 billion years to come. The massive stars live only for millions, tens of million years. That kind of life will not be enough for sustaining, for creating, first of all, the organic life and then sustaining it. Then distance on the star, or degree of circularity and tilt of the planetary orbit, existence of water on the surface of the planet. See, we are assuming that water-based chemistry is essential for life to exist and to survive. Is that true? We don't know. Life might survive, might even arise in clay. Apparently, there's a school of thought clay was the birthplace of microbial life to arise here on this planet. Chemical composition, presence of oxygen along with nitrogen in the planetary atmosphere. Next slide, please. So, however, we have seen in the extremophiles, microorganisms appear to survive the most uncongenial environment of space, ultraviolet radiation, bombardment by energetic cosmic ray particles, near absolute zero temperature. Extremophiles are found to have lived under severe conditions at the bottoms of oceans, under huge pressures. So located on ocean beds, bottom of sulfuric geysers, cores of volcanoes, polar ice caps, oceanographers have in fact discovered primitive microbes living in hydrothermal vents on the ocean floor. So we are gradually making progress. So you can't expect that our science will give us and deliver all the results we want, because Mother Nature is under no obligation to reveal all her secrets to us in this circa 2020. We will have to be patient. So it is for the future generation of young men and women sitting in the audience and listening presumably, who have to push the frontiers of exobiology forward. I hope in my lifetime we'll be able to see the appearance of an alien life. Next slide, please. Let's just run through. Next slide. Well, I was going to come to the extravagant scale of the cosmos. Let me ask, Mugdha, is it long enough so far? Or should I cut it here? What's the general reaction?
No, the general reaction is very good. Don't worry about it. You finish your whatever you have to say.
Okay. Yeah, let's go back slide, couple of slides. You see, you must realize there's an extravagant scale. Next slide, please. There's an extravagant scale of the cosmos. Cosmos is not merely our immediate neighborhood, the solar system, the planetary system. Your Earth, you're the sun, you have Pluto, you have the supply 4 light years away. Then you have the whole galaxy, and then clusters of galaxies, and then scale structure like what you see in a web-like structure. There are holes, giant voids. Okay, no, go back. Giant voids and walls. Now, these are the regions, the walls, where clusters of galaxies are taking birth. And here is the cluster in the Hubble Deep Field. Here, a picture of galaxies and clusters of galaxies far, far off, whom we had not even detected earlier. So, universe is far more. And in fact, all this, for all you know, might be an illusion. How do you know all these galaxies really are real? That might be an illusion. You know what an illusion is? This is an illusive cosmos universe. You have a distant galaxy, a cluster comes in front, cluster gravitationally lenses that background galaxy, and more number of images are created of the background galaxy. So this is the phenomenon of gravitational lensing. So if that is the elusive universe, you would never know what the far-off universe is like. Because the far-off sources are more likely to be intercepted by the foreground objects. So, next slide, please. So here is one typical galaxy, spiral galaxy, face on. And here is another galaxy probably is trying to cannibalize. Next slide, please. Here is the picture, April 2218. It's this lensed system. A cluster came in front, and the background galaxies are the blue ones, which have been imaged. So the one blue galaxy in the background, and they're all imaged. So I think that is the elusive universe. At some stage, I would like to share with you my passion for gravitational lensing and the elusive universe. What is it we are seeing? Distant objects. How can we then count them? So those are the puzzles which we are facing. I mean, there are, if I get time, tell you about standing problems in astrophysics and cosmology. So next slide. Let's run through the slides. Time is running out. So you'll ask the question, what is life? Very difficult to answer that question. The life comes in different forms, animate life, inanimate form. So world essentially is made up of the same basic stuff though. It's all based on ammonia, methane, water vapor, hydrogen, helium, carbon, nitrogen, oxygen. So if these elements are universally present, then why isn't life cosmically abundant? You see biodiversity of life on Earth, large variety of living organisms, as I said, of different sizes, from ants to elephants. Living beings also have a complex physical and chemical interaction with the environment. They consume energy, grow, and self-replicate. As we discussed earlier, a task where life has to perform. Life is basically composed of elements such as carbon, nitrogen, oxygen, molecular hydrogen, which are commonly present in the universe. So life may be based on carbon chemistry or silicon or sulfur chemistry, just to summarize, in the process directing matter essentially from disorder to order, while natural phenomena of the arrow is from order to disorder. So if that is what nature has followed, and the life as we know it has survived, because we happen to be in the habitable zone around our parent star, the sun. So the hope is such habitable zones will exist around other stars, and there seem to be extrasolar planets now in abundance which are accessible. So should we then expect that life would arise? Go on. Next slide, please. So formation of the first things, this is a huge leap from the primordial organic soup which I described of Charles Darwin to membrane-moderated self-replicating DNA-based structures. So chemical evolution is the starting point. And that's a black box then. First cell will come, and then you have biological evolution. So biological evolution, as we know it, follows chemical evolution. And Darwin's warm little pond was the chemical evolution. That's the dream of the chemical evolutionists, to create Darwin's warm little pond, which is what Miller and Urey tried to do. Next slide, please. I should not try your patience. Origin of life. I mean, maybe it's intelligent design. If you believe in divine intervention, maybe God created life, if you're a believer. I don't believe in that, but that's one point of view. A primordial soup of ammonia, phosphoric salt, heat, light, electricity. Darwin's clue of warm little pond. Or panspermia, extraterrestrial origin with asteroids, meteorites, comets coming in. They are the carriers which bring microbes and they hit the Earth's atmosphere, and eventually they appear on the Earth's surface. Or a zoo hypothesis, seedings of microbes launch into space accidentally or specially planted by external intelligent civilization. Maybe there's an intelligent civilization, we launch these microbes to see how they develop here on this planet. Zoo hypothesis, seeding of microbes launch into space accidentally or specially planted by the external intelligent civilization. Or Anthropic Principle. Anthropic Principle says that only those universes exist which have conscious observers. Does it mean if there are no conscious observers, the universe does not exist? Now, this is the anthropic view. Some people are very fond of that. Kepler, for example, okay, he is a great believer in the Anthropic Principle. So how can this come about? It can come purely by chance, very small probability though, that ammonia, methane, water vapor will come together. First of all, the ammonia has to be manufactured from hydrogen, helium, carbon, nitrogen. And then selective survival of molecules capable of creating higher forms of life and the inherent self-ordering tendencies in matter. So all these steps have to be taken care before the intelligent life arises. And now you might ask, you are saying that life arose out of these biomolecules. So basically the chemistry came out of hydrogen, helium, carbon, nitrogen, oxygen. Okay. Then where did the mind or the consciousness, if we are all biological engines made up of hydrogen, carbon, nitrogen, oxygen, helium, ammonia, phosphorus, sulfur, then at what stage did we get or inherit our mind or consciousness? There's a profound question which people like Roger Penrose and others are really addressing. In fact, I should tell you, Roger Penrose is likely to come here once we come out of this ordeal of the COVID-19, when we can ask him that question. Next slide, Vaya, please. So, search for intelligent life on hospitable planetary sites. It depends on probabilities of various kinds. Number of intelligent civilizations capable of interstellar communication, total number of stars in the galaxy, the formation that is, fraction of stars that are planetary companions, fraction of stars with habitable zones around them, fraction of planets with hospitable conditions for the development of life forms, and fraction of sites where intelligent life has evolved during the lifetime of the parent star. If the parent star were to extinguish itself in million years, life will not have time to grow. Our average lifetime of the technically advanced civilization after reaching the communicative phase. First of all, the technically advanced civilization has to be desirous of communicating with the rest of the civilizations in our galaxy, right? They may not be. I mean, life may be all right with them. So why should they bother? I think we are attributing human anthropomorphic thinking to them. But they might be quite self-contained. That's one of the reasons there's a school of thought which we haven't seen any extraterrestrial life around us. Next slide, I think, came from Vaya. Vaya, next slide. Probability of finding intelligent life in the galaxy is a very famous Drake's equation. You see, you should realize there are some 100, 200 billion stars in our galaxy, and there are likely to be millions of planetary systems. What are the chances? They all depend on various probabilities. Total number of stars in the galaxy, percentage of stars that can have planets, percentage of stars that actually have planets. Not all stars have planetary systems, planetary retinues around them. Percentage of stars with habitable zones, percentage of planets with stable circular orbits, percentage of planets where life has evolved, percentage of planets where life has moved beyond simple molecular form to multicellular structure, percentage of planets that have intelligent life of the planet and the parent star, percentage of life that avoided self-destruction. That's probably the fate of most of the civilizations, that they overpopulate themselves. Do you realize that our system here in this sun and the planets, in about 30 years, the Earth's population will double itself. In 3,000 years, the population on the Earth will be comparable with the mass of our galaxy. Now, where are we going to accommodate all of us? So, and then the duration before we take cable signals to Earth, they may not be all desirous of communicating with other civilizations. So, we call intelligent civilizations as those who are desirous to communicate. So they should reach that communicative phase. So if you take all a dozen of them, multiply them together, and keep in mind that there are 10 to the 11 sites in our galaxy. Then, if, for example, we don't annihilate ourselves, then there might be as many as million sites where life could arise in the habitable zones. If not, if we destroy ourselves, so that fact is very important. There might be only one, and that is us. That will be unfortunate, because there must be gradations of civilizations, some in our own galaxy. Next slide, please. Vaya. Next slide. I mean, I was going to say modes of communication.
I put it up, sir. Are you on this slide?
Yeah, fine. Actual physical contact, and of an astronaut. Yeah, and chance of encounter with aliens, visit of aliens, robots, etc. For all you know, they may have already visited us, and we were not advanced enough 200 years ago to be able to detect them, or they have found us primitive, or they decided to ignore us, that they are not ready yet, our population, to receive or to communicate with them. Next slide, please. Next slide. Vaya. So discovery of the next slide, still further. One more slide, yeah, go ahead. Forget about UFOs. So you see the vast, the slide before, vast cosmic distances make it impossible for person-to-person contact. It's going to be civilization-to-civilization contact, culture-to-culture contact. So vast cosmic distances make actual physical contact rather improbable with present-day technology. However, possibilities of communication over radio frequency exist, particularly over the microwave band around 1420 megahertz, which is the hyperfine transition of neutral hydrogen, which is the most abundant element in the universe. Okay, so SETI, Search for Extraterrestrial, is a citizen science project, network of computers around the world, and they're all trying to listen in, look for signals. Who knows if millions of SETI workers, citizen scientists, keep looking, one day signals might arise and arrive here, or maybe they're already here and we have not made the mental effort to decipher them. They are going to be narrowband signals like our radio or television. So they might be hidden in a huge data files. So we have to pull them out. That's our next slide. Let's run through those slides quickly. Here is, we had announced our presence to the cosmonaut. Pioneer 10, carried this plaque. You may have seen it already. showing a man and a woman. This is what Carl Sagan's wife, Linda Sagan, had designed for Pioneer 10. So fortunately, we have announced our presence to the Earth, on the Earth to the cosmos, to the universe at large. Because if all of us were to listen in and no one transmitted, we'll each come to the conclusion that we are alone in this galaxy, which is not the case. So it was good that we announced that Sun, Mercury, Venus, Earth, Mars, Jupiter, and the satellite has come from the Earth, and man and woman, and it shows the hyperfine transition of neutral hydrogen, which is the 1420 megahertz. Next slide, please. So this is a point I would like to emphasize. So there are going to be gradations of extraterrestrial civilizations. Out of these millions of sites, some would be million years in our future. Some would be million years in our past, in the Stone Age. Some would be 1,000 years ahead, some 1,000 years behind, some 100 years ahead, some 100 years behind. I think ideal strategy for us would be to try and get in touch with those who are 100 years ahead of us, because they may have followed a difficult road ahead. See, question the dicey issue of overpopulation, or capturing, of getting over cancer and such disease, or virus which are invading the earth now. They may already sort it out. So such civilizations which are 100 years in our future may be benevolent towards us, and they might say to us, avoid self-destruction. Because that may be, as I said, the fate of most of the societies after they reach the communicative phase. They probably destroy themselves by overpopulation of biological or chemical warfare, okay, as we are trying to do now with the COVID-19 virus going around. So they would probably help us out. Next slide, please. So we have to contact civilizations that are technologically just 100, 200 years ahead of us. Societies may be benevolent societies, especially if they have themselves benefited from messages received from outside. Advanced communities that have followed a difficult road ahead, difficult path in the development, are likely to anticipate our difficulties and send messages advising us how to avoid self-destruction. Possibly, as I said, that's a common fate of society shortly after reaching communicative phase. So we should merely not wait to receive signals, but also send out our signals, which we have done, right? Pioneer 10 plan. Next slide, please. Let's run through the next slide. So there is likely to be in my, no, wait, go back. Go back by here, please. Yeah, there's likely to be a galactic club of advanced civilizations where they know how to spot communities like us, induct them into the galactic club and help us. And there's going to be a galactic library containing, wisdom of countless civilizations, in their culture, their progress, their development. And we should access these galactic libraries. And we should certainly access and seek the membership in the galactic club of advanced civilization. Next slide, please. So maybe we are alone in the universe for all we know. For Kepler, we have not had visits from interstellar travels yet. But of course, absence of evidence does not mean evidence of absence. For all you know, the Earthlings may not be all that interesting to extraterrestrials. Maybe, perhaps we did have visitations in the past when our society was not sufficiently advanced to be receptive or worthy of their attention. Very likely extraterrestrials do not have the anthropomorphic view too, and are quite self-sufficient and may not be too keen on befriending us or fraternizing us. Next slide, please. We're almost coming to the end, I hope. So human beings, you might note, are probably inevitable products of a grand cosmic evolutionary scheme set into motion with the birth of the universe when hydrogen, helium were formed, right? We started from there when the universe was launched. Then came carbon, nitrogen, oxygen in stars, which are essential for our life survival. So we may be members of a much larger family of living beings, some of whom may have unimaginable capability. Next slide, please. Such societies might serve only momentarily, for example, might survive only momentarily in time compared to the lifespan of the years. You see, we are an inconspicuous speck of dust in this universe. But there is an important feature that we are providing the link between the cosmic past and the cosmic future. And whatever knowledge we have accumulated, we are going to transmit it to the galactic club around us, civilizations around us, not only in our solar system, but outside the extragalactic domain too. So nevertheless, we provide necessary links between the cosmic past and the uncharted future. So that's the obligation which we have, to pass on the knowledge which we have accumulated. They can only add to that. Next slide, please. Only last but one. Yeah, the last one. That's a quote from Rigveda, which I borrowed from Vaya. In the beginning, love arose, which was the primal germ cell of the mind. The seers searching in their, that is the sages searching in their hearts with wisdom, discovered the connection of being with non-being, animate with inanimate. Who really knows? Who can presume to tell? Whence was it born? Whence is its creation? Or even the gods came after its emergence. Who created the gods? Of course, humans and the sages. Okay? Who can tell from whence it came to be? Oh, that out of which reason, whether it held firm or it did not, she who surveys it in the highest heaven, maybe she surely knows. Or perhaps she does not know. Friends, thank you for your patience. Mugdha, that's the end.
Yes, sir.
I think we should clap, really.
Yes.
Oh, no. I can't see them clapping, so.
Yeah.
Oh, you can see them if they turn on their videos. Thank you so much, sir.
Oh, I hope it was intelligent. Was it intelligible?
Yes, sir. There is a question for you which says, what is aperiodic complexity?
Oh, why I should reply to that?
Yes, sir. So what happens? Yes, no, sir, it's not my word. What happens is that we have crystals are periodic complexity.
It's not periodic.
Yeah. So what is not periodic is aperiodic complexity. Yes, sir. So
yeah,
that is
crystal system is always periodic,
yes,
while crystals, if you go to fluids, they are not, repeating their structures.
Exactly.
Or crystalline, or not periodic, and fluid is aperiodic, if you like. But
yes,
in fluid system, there are some which are semi-periodic.
yes,
So aperiodic is one which is not periodic.
periodic.
I guess. Right?
Yes, yes, sir. The next question is, what is Tebis star?
What is what?
Tebis, T-A-B-B-I, Tebis star. Tebis star. I'm not very sure about what it is.
I haven't heard.
Yeah,
I've not heard about it. Has the questioner understood which that star is?
No. So there is this. Amod, you'll have to give more on a question. The next question is, can life start on a body other than a planet, say on a comet?
Well, yeah, comets do carry microbes. So there they are, microbes. On meteorites, we have found microbes. So comets, meteorites, they are minor bodies in the solar system, okay? And cometary tails certainly carry microbes. Microbe is a form of life, not the advanced form of life perhaps, but form of life.
The next question is, what is our degree of readiness to make contact with extraterrestrial life?
Oh, we are always now we have reached a communicative phase. See, you can contact others only if we had means of communication. So we have mastered radio techniques, we have radio telescopes, we have radars, so we can communicate with any civilization which is similar to ours, if they are willing to receive our signals. So we are in a position now, and we certainly have advanced enough to be able to communicate on the radio band or microwave band with any civilization in our own galaxy.
Okay. The next question is Area 51 legitimate?
Is what?
Area 51, where Americans are supposed to have found and captured an extraterrestrial being and stuff.
So, such a soft evidence, Bermuda Triangle, I wouldn't take it serious, just as I don't take UFOs, unidentified flying objects, or chariots of God, or found Danicans very seriously. And whatever the sighting, very soft evidences, military crafts flying at the altitude of 15 miles, 20 miles. So they are all the time crisscrossing the skies and then don't reveal to you their flight paths. So I think those are many times misunderstood by people as, extraterrestrial bodies, but they are not. See, if the extraterrestrial body were to come here, wouldn't you imagine a fast-moving vehicle will make sound going through the Earth's atmosphere? Anything, pressure fluctuations arising from the motion of the body, okay, presumably this object is coming down into the Earth's atmosphere, otherwise we won't be able to spot it. It will make noise, aerodynamic noise. Does that answer it?
Yes, sir. Yes, sir. Yes, sir. The next question is, how do we communicate with our sense of left and right to an alien?
Oh, that's the helicity.
Yeah, helicity.
That's the helicity. Yeah, because there are, for example, Murchison meteorite, where Cyril Pannaparama in Australia, in Murchison place, discovered 17 amino acids. Okay, and they are supposed to be of terrestrial origin because of the helicity. Yeah. Life everywhere is not in the helical form of the kind we know, left to right. Some of them have right to left. Okay. Helical structure. You know what I mean? Helical structure,
yes,
going left to right and then right to left also. So the Murchison amino acids are considered to be extraterrestrial because their helicity was opposite to ours.
So, what is Denickson's theory? I'm not so sure what it
is. Whose theory?
Eric von Denickson.
Oh no, the Eric von Daniken.
Daniken.
So, Eric von Daniken, wrote that book, Chariots of God. He also attributes, that's the author, he attributes extraterrestrial life to those who have come here, either in unidentified flying objects or in chariots.
Chariots of the gods, yes.
That's what chariots of the gods. I don't take those evidences seriously, but maybe that's my bias.
You missed, you avoided talking about that slide, pseudoscience and all such things.
Yes. But, shall we go back? Shall we go back to that?
Sure.
So you want to go back to yes, sir. Yes, sir. Yes, sir.
Yeah, UFO, pseudoscience.
Yes, sir.
I didn't want to get diverted.
Would have automatically come in. If you have to believe in
this one, sir.
Yeah. So discovery of identifiable artifacts of extraterrestrial design is one way. For example, quite a few people, the gullible types, believe in unidentified flying objects. See, many times these UFOs are really military contraptions which are not revealed. High-flying aircraft or meteoritic remnants, okay, which are coming through the Earth's atmosphere. These are pseudo-scientific beliefs, remember. See, scientific belief demands hard evidence. And science works on the principle that I should be able to repeat the experiment. So some archaeological relics, for example, pyramids, some people think were left over by aliens. Oh, these are left as visiting cards by aliens, I'm saying. So I think some inadvertently leaking signals, such as radio and infrared emission from the inhabited planets, I would take more seriously. So we have to remotely sense the existence. For example, advanced civilization would have industrial complex. From industrial complex, you would have infrared emission. This infrared emission excessively coming out from a site would be a telltale sign that there is, an advanced civilization operating there. That was Phil Morrison's theory.
And the famous Dyson sphere.
And Dyson sphere too. So Dyson, Morrison, they were the thinkers. You see, I met Morrison, actually I stayed with him in MIT. And it was a delight to talk to him because he had so much, because he was the prime mover for SETI project. He got money from them at that time, 50 years ago probably. And, he came to TIFR. Do you remember?
No, sir.
No. And then Daniel and I, we went and saw him. We had a long session with him. And he mentioned the names of Carl Sagan and Chet Shostov and those people who were then getting the project. So search for extraterrestrial intelligence, I would take very seriously. But frankly, the bias, you might say, UFOs and others are pseudo-scientific beliefs. Don't take them too seriously. These are soft evidences. Science demands that you must produce evidence which you and I should be able to reproduce. You might say, how do I reproduce a flying aircraft? It just goes by. Okay? But then that is soft evidence. Science and scientific experiments, they should be always reproducible. This is what Karl Popper, the great historian of science, said. Any good theory should be falsifiable. If I give a theory, it should be falsifiable. Then only. You don't come and tell me UFOs we have spotted and maybe they are the travelers coming from extraterrestrial sites. I would say, yeah, get lost.
Yes. Yes.
But that's a bias of mine.
But that
all we know, they might hear already, and you and I may not have made the right, mental exercise to be able to recognize or identify them. How do you know some of them are not, living here? If I see some of the weird ones, then I sometimes think they probably are from outside.
That is true. That is true.
You come across many of them.
Yes, you do. There is one question which says, given, sir. There is one question which says, given the fact that civilizations are more advanced than ours, have not contacted us in the way that we decipher, we can comprehend, does it not make sense to wait and not contact the advanced civilizations?
Oh, no. We should always be A, willing to receive signals, A, and B, you see, the cosmic distances are so vast that signals sent 1,000 light years away is going to take 1,000 years to arrive here. Or maybe some signals did arrive here 200 years ago, where our technology was not advanced enough to receive them. Now we have powerful radio telescopes, GMRT, UT, which can pick up signals coming from outside. So, or Arecibo in the United States. So I think what you have to realize is that the technology will keep advancing. Remember, 50 years ago when I was doing my research in Cambridge, the technology had not advanced. And look, in 50 years, we have seen the golden age of astronomy. And if anyone asks me, has astronomy any future? I would say yes, of course. It has plenty of future because technology has advanced. And with technology comes the advancement of the fields. Look, who would have thought of the CCDs? Who would have thought of space missions whereby you can observe distant Hubble telescope, observing deep fields, ultra deep fields.
Gravitational fields.
Yeah, you're pulling out galaxies which you didn't even know existed in that part of the universe.
Sir, sorry. Please, sir, please go ahead, sir.
No, you go ahead.
No, so I was going to the next question.
Please.
So next question says that there is a mention of time dilation scenario in Mahabharata where a king Kakudmi does interstellar travel and discovers time has passed differently for him while during his travel to another planet. Is it possibly true, or the interpretation is false?
It's a myth.
It's a myth.
See, many of these legends, have come down to us. We should not take them very seriously. You see, like the aircraft, Pushpak, was supposed to have existed in the times of what, Ramayana?
Ramayana, yes, sir.
Ramayana.
Yes.
I shouldn't take it seriously. If one were to take very seriously such records, you see, they are legends. Don't forget. Ramayana and Mahabharata were written by sages, very wise men. See, Mahabharata.
The foundation. If a copy of Asimov's Foundation series is found, say, 3,000 years later,
yes,
they may say that he knew it.
Yes.
Exactly.
Yes.
It's a good example.
But
yes.
How far do you take that seriously? Is that corroborated? I mean, aircrafts, for example, how far the technology was advanced in those days to be able for us to take that seriously? Maybe they were advanced, and we have not made the mental effort to appreciate that. What do you think? You have to now make me wiser.
Yes, sir. That's true. So that is the last question, sir.
Okay, any good scientific questions? So far I have not heard one, except for one or two.
Yes, so somebody wanted to know the difference between hard evidence and soft evidence.
Oh, soft evidence is like, unidentified flying object, the chariots of God, like.
Somebody saw it.
Or pyramids being built by aliens. That is soft evidence. Yeah. Hard evidence is where I should be able to reproduce the experimental results. Anything, I should be able to falsify it equally. A good theory or experiment is one which is falsifiable. Take this message home.
So, that's about all, sir.
Okay, I'm sorry, I bored you. Mugdha, was it?
And I am taking up your offer of another lecture.
Oh, I think you have had enough. You have had enough now.
Zoom and everything, so it will be easier.
How was it coming through, though?
It's good. Only now you should learn how to handle your own PPTs. That's it.
Yes, that's it. I should. Why didn't it appear here? I should have been able to handle it here.
Yes, sir.
One of us will come and show you. Or if you start going to CBC, somebody can show you. That's not a theoretical.
I should be. Yeah, I should be able to see it here on my iPad.
Yes, sir.
It must be there somewhere.
It must be.
Thank you, sir. Very interesting.
Or maybe it is. Oh, by the way, you are very welcome to keep the PPT in your record.
Oh, thank you, sir.
And it is for free disposal. Free circulation, free disposal.
Yes. Thank you, sir.
Well, thank you, Dhanashri, for listening to me so long.
If you have...
how many of them were there?
36 were there, now there are 33. There are some network drops and all.
So what message do they take home? Let's ask them. At the end of it, what message they take home? Do they believe in the existence of extraterrestrials? Do they believe we'll be able to communicate with them? Do they believe that extraterrestrials will benefit us by giving information about the advanced technology or capturing of incurable diseases? What is the belief? Maybe.
Nobody is...
I believe it would be such a waste of space.
Yeah.
Went off.
Someone says to me, Rama Krishna, she believes, he or she, that there are extraterrestrials.
Tanike says it
be optimistic.
Space if they were, we were the only ones to exist in the universe.
Yes.
It's not waste of space. Maybe it was just for us.
It would be great. I'm not sure either way, someone says. One before that says that it's a metaphor.
Yes, sir.
Let people express their views.
Sure.
Even
Believe
by typing.
Of them, isn't it?
Anyway, it's an enthusiastic crowd, I hope.
Yes, sir.
Oh, the universe is so vast that it will be some supreme.
It would be arrogant to think that we are alone. Yes, sir. The general vote is in favor of extraterrestrial life.
I mean,
can you
suppose if I present to you a premise that probably they had visited us already 200 years ago and did not find it technically advanced and went away. I wish I could record. Sorry?
No, I'm asking who is the institution host today? They could have created a poll for you. And
yeah.
So can I ask you a question?
Please.
My name is Ramakrishna. Yeah, I just wanted to ask you, are there any experiments being conducted to recreate life with different waste chemicals, like you said, ammonia and sulfur?
Oh, yeah. For so many people are trying to recreate Darwin's one little pond. You see, the evolutionary theorists, okay? I mean, there are some who don't believe in evolution, unfortunately, okay? Because they believe in, I gave that hint to you, divine intervention, grand design. What do you call it? Grand design, right? So now I'm a great believer that life arose out of chemical evolution. Biological evolution followed chemical evolution, and coming together of ammonia, methane, water vapor, as Darwin's warm little pond demonstrated, and phosphoric salts, heat electricity, is not an unlikely event. Maybe the probability is small, 1 part in 10 to the 40, 10 raised to 40, but nevertheless, finite probability. And maybe things arose. So, some message flashed by.
But our Dr. Craig Venter has already created a DNA, artificial DNA.
Who went higher?
Craig Venter.
Yeah.
The
by the way,
Wilson and
Collins. Yeah. You know, I'm sad to tell you that one of the exobiologists from BRC, Mohinder Singh Chadha, he passed away 2 days ago. It was he invited Cyril Pannamparuma and some of us, Obed Siddiqui, Cyril Pannamparuma, Pushpa Bhargava, and we had a conference along with Daniel on chemical evolution of elements and evolution of life. So my job was chemical evolution of elements. And the conference was so exciting. And Pannamparuma was in elements telling us about the Murchison meteorite with 17 amino acids of non-terrestrial origin. So those were the days. We are losing one by one some of my old friends. Siddiqui is gone. Pushpa Bhargava is gone. Pannamparuma is gone. So that is life.
So a follow-up to the previous question. If we could actually, if there have already been experiments to recreate life, has there been experiments to create consciousness in beings?
No, no. You see, as it is so difficult to create or recreate Darwin's warm little pond and the chemical evolution. Chemical evolutionists are trying very hard to create, but they can create amino acids, proteins, but they can't create biologically replicating life, self-replicating life. And more importantly, put consciousness and mind in that. At what stage? I have a crazy thought. My thought is, see, if you say that we are biological engines, okay, biological engines which inherited the raw material from the early stages of the creation of the universe. And in the first 3 minutes, as I've been saying, Stephen Weinberg's objective that you inherit hydrogen, helium, light elements from there. Then initially, even before the elements came, there was cosmic energy. Energy came first. Out of the energy came matter. Okay? That energy, see, surely then our biological engines, as we are, human beings, must have inherited not only the biological molecules, but almost certainly a good fraction of the cosmic energy too. Now, what do you call the cosmic energy then? Is that your mind? Is that your consciousness? Is that your soul? Call what you may. What's your choice?
Okay.
You listeners, what's your
sessions? We should have captured you for 2 hours, but that was my mistake.
No, but
we have to end this session.
Oh, people must have evaporated now.
So,
no
there, but now we have to close the session because there is another session.
Just one last question, ma'am.
One last question.
No, sorry.
Is the mind an imprint of DNA?
Please close the session. Dr. Chitre, thank you very much.
Oh, you're very welcome. You're very welcome.
Is there an email address to contact?
Thank you for Mayank.
Yes, ma'am. I'm here. My pleasure. Entirely my pleasure. Entirely my pleasure.
Well, thank you, Mayank.
My pleasure, sir. My pleasure.
Thank you
Entirely my pleasure,
for inviting me.
That was a very wonderful lecture, sir. Thank you very much, sir.
Thank
you, sir.
My first attempt for webinar.
Oh, sir.
Yeah,
no, it went off wonderfully, sir.
You inducted me, and Mukta Karnik encouraged me.
Sir.
So you need mentors like that.
No, sir. It is our privilege to have you over here, sir.
All right, then. We sign off. Sign off.
Yes, sir.
Thank you.
Thank you.
Thank you, sir.